Assalamu alaikum. My presentation topic is KNNBZT lead free material. It stands for potassium, sodium, niobium, barium, zirconate, titanate lead free material. Firstly, I will explain the abstract of my presentation. The global urgency to replace lead-based piezoelectric materials, specifically lead zirconate, titanate, PCT, is driven by the severe environmental and physiological toxicity associated with lead oxide. Among the most promising lead-free alternatives, potassium sodium niobate (KNN) modified with barium zirconate titanate (BZT) has emerged as a high-performance system capable of bridging the property gap historically dominated by lead-containing ceramics. The analysis delves into the fundamental chemical mechanisms involved in solid-state synthesis, including carbonate decomposition, kinetics, and intermediate phase formation. A rigorous step-by-step synthesis methodology is presented alongside advanced sintering techniques such as two-step sintering and spark plasma sintering. Furthermore, the integration of artificial intelligence and machine learning in accelerating compositional design is explored, highlighting how data-driven models optimize the piezoelectric coefficient and thermal stability. Basically, it identifies critical technical challenges, offers strategic future recommendations, and detailed daily life applications in medical and industrial sectors. Finally, a comprehensive mapping to the United Nations Sustainable Development Goals (SDGs) validates the transition to lead-free technologies as a cornerstone for responsible consumption, industrial innovation, and global health preservation. Introduction to lead-free piezoelectric evolution. If we talk about the history of piezoceramic, piezoelectric materials, then the history of piezoelectricity or pressure electricity traces back to its discovery in 1880 by Jacques and Pierre Curie, who identified that certain natural crystals such as quartz, silicon dioxide, tourmaline, Tourmaline, a natural crystal, its formula is complex due to variations, but the general structure is I have written here XY3 Z6T6018 BO3 BO3 V3 W, where X, Y, Z, T, V, and W represent different elements like sodium, calcium, magnesium, aluminium, silicon, boron, hydroxyl, fluorine, and oxygen. And Royal salt, also known as potassium sodium tartrate tetrahydrate, has the chemical formula as I have written here: potassium sodium C4H4O6 and tetrahydrate 4 water molecules. Basically, these certain natural crystals generated electrical charges upon mechanical deformation. While early applications during the First World War utilized these materials for sonar, their hygroscopic nature rendered them unstable for broader industrial use. The mid-20th century marked a paradigm shift with the discovery of barium titanate during World War II, followed by the breakthrough of lead zirconate titanate (PZT) in 1952. PZT quickly dominated the market due to its exceptional electromechanical properties, facilitated by its unique morphotropic phase boundary, where the coexistence of rhombohedral and tetragonal phases allows for high levels of polarization rotation. Despite its technological dominance, PCT contains over 60% lead oxide by weight, a substance categorized as a dangerous compound with carcinogenic and neurotoxic properties. During the calcination and sintering stages of manufacturing of the PCT material, lead oxide is highly prone to volatilization, causing direct environmental contamination. At the end of device's life cycle, improper disposal leads to lead leaching from equipment into soil and water systems, ultimately impacting human health, particularly in vulnerable populations such as children. These concerns have led to these concerns have led to stringent international regulations such as the European Union's restriction of hazardous substances ROHS and regis- and registration, evaluation, authorization, and restriction of chemicals REACH directives, which have increasingly tightened the allowable lead content in electronic materials, recently aiming for a limit reduction from 0.1% to 0.05%. So, the search for lead free alternatives has focused on three primary families: alkaline niobates, bismuth based perovskites, and barium titanate based systems. Among these, potassium sodium niobium oxide KNN is recognized as to replace PCT for high performance applications. The 2004 report by Seto, which demonstrated high piezoelectric activity in textured KNN based ceramics, ignited a research boom that continues to push the boundaries of lead free materials. The modification of KNN with PCT has specifically enabled advancements in energy storage density, optical transparency, and piezoelectric sensitivity, making it a critical focus for both academic and industrial researchers. If we talk about what is KNNPCT, lead-free material, firstly, potassium sodium niobate, barium zirconate, titanate, represented as I have written a formula here. It's basically is a lead-free perovskite solid solution system developed as an environmentally friendly alternative to lead-based piezoelectric such as PCT. It combines the high Curie temperature and strong piezoelectric properties of KNN with the excellent dielectric response of BCT. This energy produces enhanced electromechanical coupling, making KNN-BCT one of the most promising lead-free candidates for sensors, actuators, and energy harvesting devices. Basically, it's based on the solid solution between potassium sodium niobium oxide KNN and barium zirconium titanium oxide BZT, both having a perovskite crystal structure, which I will explain later. Moving forward, KNN provides a high Curie temperature for 20 degrees Celsius. The Curie temperature is the temperature at which a material loses its natural electric polarization and stops behaving as a ferroelectric. Below this temperature, the material is ferroelectric and can generate or respond to electric charges. But above this temperature, it becomes paraelectric and behaves like a normal nonpolar material, normal dielectric, while BZT enhances polarization is when the positive and negative charges in a material separate slightly, creating a small electric field inside the material. Also, BZT enhances dielectric response. If we talk about what is a dielectric response that BZT enhances in KNN BZT material, dielectric response basically, dielectric is a non-conductive material that can store electrical energy by polarizing when an electric field is applied. It doesn't allow current to flow like a conductor. The polarization creates an internal electric field that opposes the applied field, storing energy. KNNBCT, sodium, potassium, sodium, niobium oxide, barium, zirconium, titanium oxide is a lead-free piezoceramic with a perovskite AbO3 structure exhibiting orthorhombic tetragonal phase coexistence near room temperature. It shows high piezoelectric performance with D33 piezoelectric constant values, typically in the range of 300 to 600 picocoulombs per Newton. The material possesses good dielectric properties, 800 to 2500, with low dielectric loss and stable frequency response. KNNBCT also exhibits strong ferroelectric behavior. Its Curie temperature 300 to 420 is higher than many lead-free alternatives, ensuring good thermal stability. Importantly, KNNBCT is environmentally friendly, fully lead-free and compliant with ROHs. KNN, now separately, if we talk about what is KNN and what is BCT, firstly, I will explain KNN. KNN, potassium sodium niobate, with the chemical formula K 0.5 and sodium 0.5 niobium oxygen, is a widely studied lead-free piezoelectric ceramic. If we talk about the structure of KNN, A site, potassium and sodium 50-50 ratio monovalent ions providing charge balance and influencing lattice size. B site, cation, niobium forming niobium oxide octahedra responsible for ferroelectric polarization. At B site, niobium present at the center of octahedra. Oxygen ions occupy the corner of the octahedra, linking B site cations to form the perovskite network. As shown in the figure, crystal structure of pure KNN. Potassium and sodium ions are present at the corners of cubic crystal, and niobium ions are present at the center of octahedra, and oxygen ions occupy the corners of octahedra that link B site cations to form the perovskite network. KNN exhibits a high Curie temperature, making it suitable for high temperature applications. At room temperature, it typically shows an orthorhombic ferroelectric phase. KNN demonstrates good piezoelectric, dielectric, and ferroelectric properties compared to other lead-free systems. Now, what is piezoelectric property? Basically, the property that convert mechanical stress into electrical energy. The ability of a material to generate electric charge when mechanical stress is applied, or conversely change shape when an electric field is applied. Example, KNNBCT generates voltage when pressed or bends when voltage is applied. Dielectric property, it stores electric energy. The ability of a material to store electrical energy when an electric field is applied. KNNBCT can store charge like a capacitor. It's example of dielectric property. Now moving forward, ferroelectric property. It's basically reversible spontaneous polarization, the ability of a material to have spontaneous electric polarization that can be reversed by an external electric field exists below the Curie temperature. Example of ferroelectric property like potassium, sodium niobate, barium, zirconate, titanate material can switch polarization direction when voltage is applied useful for memory and actuator applications. Potassium sodium niobium potassium sodium niobate piezoelectric coefficient is moderate but can be significantly enhanced by doping or solid solution formation. A major challenge of KNN is alkali volatility during sintering, which affects densification. Despite this, KNN is considered a key base material for developing advanced lead-free piezoelectric ceramics. Now, moving forward, if we talk about BCT, it's a barium zirconate titanate, typically refers to the solid solution which crystallizes in the perovskite AbO3 structure. The structure of BCT is here A side cation barium a divalent ion stabilizing the perovskite lattice and influencing lattice constant. B side cations titanium and zirconium substitution of titanium by zirconium tunes ferroelectricity. Oxygen ions form BO6 octahedra connecting the lattice. As shown in the figure, crystal structure of PCT, oxygen ions are present at the corners of octahedra and titanium and zirconium ions are present at the center of octahedra and barium divalent ions are present at the corners of crystals that influence lattice constant and that stabilizing the perovskite lattice. Zirconium concentration matters a lot. For low zirconium content, BCT exhibits a tetragonal ferroelectric structure similar to barium titanate. As zirconium concentration increases, the structure gradually evolves towards a cubic or pseudo-cubic symmetry. Zirconium substitution increases lattice distortion and disrupts long-range ferroelectric order. The structural flexibility of PCT plays a key role in enhancing piezoelectric properties when combined with KNN. Now, the formation of potassium sodium niobate, barium zirconate, titanate, lead-free material. The formation of this piezoceramic material is generally achieved through a solid-state reaction route. Although other methods also follow the same fundamental chemical principles, but the main method that is used is solid-state reaction route. The formation process involves carbonate decomposition, oxide reaction, diffusion controlled perovskite formation, and solid solution stabilization. Raw materials for the synthesis of KNNBCT piezoceramics. The synthesis of piezoceramic material requires high purity oxide and carbonate precursors to ensure phase purity, compositional control, and reproducible piezoelectric properties. These materials react through carbonate decomposition and solid-state diffusion to form the KNN-BCT perovskite solid solution. If we talk about the raw materials that are needed for the production of for the synthesis of KNN-BCT piezoceramic, first type A-side precursors that include alkali and alkaline earth metal, alkali and alkaline earth ions, potassium carbonate that is source of potassium A-side cation in KNN that I have explained earlier, sodium carbonate source of sodium A-side cation in KNN, and barium carbonate source of barium A-side modifier from BCT. If we talk about a second type of raw materials that are required for the synthesis of KNNBCT piezoceramic are niobium pentoxide, titanium dioxide, zirconium dioxide, and other optional additives are also needed for property tailoring that use depending on desired electrical behavior, such as manganese oxide, iron oxide increase mechanical quality factor that are for hard ceramics, and lanthanum oxide, tantalum pentoxide that increase piezoelectric coefficient that are used for soft ceramics, and sintringates, cuprous oxide, zinc oxide, and lithium carbonate lower sintering temperature and improve densification. The process that involve in the synthesis of this piezoceramic material, the first step is pre-processing moisture control. Alkali carbonates like potassium carbonate, sodium carbonate are highly hygroscopic, absorb water from the air. Raw materials are dried in an oven at 200 degrees Celsius for 24 hours. Failure to do this leads to incorrect stoichiometry, as the weight would include water rather than pure chemicals. So pre-processing is very important. Moisture control is compulsory. Second step is stoichiometric weighing. These powders are stoichiometrically weighed according to the desired KNNBCT ratio and mixed via wet ball milling, typically in ethanol or isopropanol, to ensure chemical homogeneity and intimate particle contact. The purpose of this step is to achieve uniform cation distribution and reduce diffusion distance in later steps. Step 3 in the synthesis of KNNBCT material is primary ball milling homogenization. Mechanism of this step is mechanical energy breaks down clusters. Powders are mixed with zirconia balls in a medium like anhydrous ethanol. If we talk about the time for this step, 12 to 24 hours to ensure that barium and zirconium ions are perfectly distributed among the niobium and sodium particles. Now, next step is calcination phase formation. Basically, calcination is a high temperature process where a material is heated below its melting point to bring about thermal decomposition, phase transformation, or removal of volatile components. In ceramic synthesis, calcination decomposes carbonates, potassium carbonate, sodium carbonate into oxides, forms the perovskite AbO3 phase, removes moisture or organic residues. This is where the solid state reaction occurs basically. If we talk about the conditions, typically 850 degrees Celsius to 950 degrees Celsius for 4 hours, and outcome of calcination is CO2 is driven off and the atoms rearrange into the AbO3 perovskite structure. First stage of calcination is thermal decomposition of carbonates. Upon heating a 600 to 800 degrees Celsius, alkali and alkaline earth carbonates undergo endothermic decomposition, releasing CO2 gas. Decomposition reactions are as showing here. Potassium carbonate decomposed into potassium oxide plus carbon dioxide is evolved. Secondly, sodium carbonate converts into sodium oxide plus carbon dioxide, and barium carbonate, barium oxide, and carbon dioxide. This step generates reactive metal oxides, potassium oxide, sodium oxide, and barium oxide, which are essential for perovskite formation. Critical issue during stage 1 is potassium oxide and sodium oxide are volatile, requiring careful temperature control to avoid alkali loss. Calcination stage 2 is formation of primary perovskite phases. At higher calcination temperatures 800 to 900, solid state diffusion reactions occur between oxides leading to primary perovskite phase formation. Formation of KNN phase involves potassium oxide react with sodium oxide and niobium pentoxide and potassium sodium niobate is formed. Here, potassium and sodium occupy the A site in the perovskite structure, niobium occupies B site, and oxygen forms the corner sharing niobium oxide octahedra. And formation of PZT phase, barium oxide plus titanium oxide plus zirconium oxide, these combine to form BZT, barium zirconate titanate. Basically, the mechanism involved in the synthesis of piezoceramic material is solid state diffusion of cations, rearrangement into the AbO3 perovskite lattice. Solid solution formation of KNNBCT during prolonged calcination and subsequent sintering barium, zirconium, and titanium ions diffuse into the KNN lattice, forming a single phase solid solution. As shown in the reaction, uh, KNN and BCT combine and form the reactants combine and form a KNNBCT solid solution. Site occupation A site potassium and sodium partially substituted by barium, niobium partially substituted by titanium and zirconium. This substitution induces lattice distortion and structural instability, which is essential for phase boundary formation. Kinetic stages of calcination. Research into the calcination kinetics of lead-free precursors identifies four distinct stages of chemical evolution: stochastic nucleation, phase boundary reaction, bulk chemical reaction, and final phase boundary reaction. In stochastic nucleation, this initial stage involves the decomposition and dehydration of reactants. Basically, in stochastic nucleation, decomposition and dehydration of reactants occur, followed by the emergence of the first perovskite nuclei. Secondly, phase boundary reaction. This reaction proceeds at interfaces between reacting particles, often limited by the contact area between the diffusing cations. Hence, kinetics are controlled by these processes. Bulk chemical reaction, characterized by a deceleration in the conversion rate as the intermediate phases are consumed and the primary perovskite structure dominates. Final phase boundary reaction, the completion of the reaction and the stabilization of the pure phase, typically requiring precise temperature and time control to avoid secondary phase formation. After calcination, next step for the synthesis of KNNBCT material is compaction and pelletizing. The calcined powder is remilled often for 4 hours to break up agglomerates. A binder like polyvinyl alcohol is added to improve the strength of the green bodies. Pellets are pressed at 75 to 80 megapascal and subsequently subjected to cold isostatic pressing at 240 to 300 megapascal for 5 minutes to achieve maximum green density. Next step is sintering strategies. Basically, sintering involves densification of the material. Densification of calcined material like sintering is the most delicate stage of synthesis. Several methods are utilized to achieve densities exceeding 95% of theoretical density, but conventional sintering, two-step sintering, and spark plasma sintering are explained here. Sintering at In conventional sintering, sintering at 1050 degrees Celsius to 1150 degrees Celsius for 2 to 4 hours. Pellets are often buried in packing powder of the same composition to create a local alkali rich atmosphere that suppresses evaporation. Two-step sintering In two-step sintering, the sample is heated to a higher peak temperature T1 for a very short time and then cooled to a lower temperature for a long time. This suppresses the rapid grain growth that usually degrades piezoelectricity. In spark plasma sintering, it basically utilizes pulsed direct current and pressure to achieve rapid densification in minutes rather than hours. This significantly limits alkali volatility but may result in very small grains that require post annealing to optimize properties. And the last step is polling to activate the piezoelectric effect in the material. The sintered ceramic are polled in a silicone oil bath at temperatures ranging from room temperature to 120 degrees Celsius. A DC electric field, typically 3 to 5 is applied for 15 to 30 minutes to align the domains in a single direction. Final product, the resulting KNNBCT piezoceramic exhibits high piezoelectric, dielectric and ferroelectric properties ready for applications. If we talk about the thermodynamics that involve in the synthesis of that involves in the synthesis of material like KN BCT formation governs whether the desired perovskite phase forms and remains stable during calcination and sintering. Driving force gives free energy, enthalpy, entropy, phase stability, volatility considerations, and solid solution formations involve thermodynamically control whether the desired perovskite phase forms and remains stable during calcination and sintering. Driving force gives free energy. Formation of KNNBCT is thermodynamically favored when the Gibbs free energy change becomes negative during calcination. High temperature lowers Gibbs free energy, enabling the solid state reaction between carbonates and oxides to form the stable perovskite phase. Enthalpy: the formation of strong niobium oxide, titanium oxide, and zirconium oxide bonds in the AbO3 perovskite lattice releases energy, making the reaction exothermic after carbonate decomposition. Entropy: decomposition of carbonates increases entropy due to gas evolution, further stabilizing perovskite formation at elevated temperatures. Phase stability: proper sodium, potassium, sodium, barium, zirconium, titanium ratios minimize free energy differences between orthorhombic and tetragonal phases, enabling polymorphic or morphotrophic phase boundary stability essential for high piezoelectric performance. Volatility considerations: thermodynamically, alkali oxides have high vapor pressure at sintering temperatures, increasing free energy and destabilizing stoichiometry, requiring excess alkali addition or controlled atmospheres. Solid solution formation: substitution of barium ions at the A site and zirconium titanium at the B site lowers lattice strain energy, stabilizing the KNNBCT solid solution. Thermodynamically, KNNBCT formation is driven by negative Gibbs free energy, strong metal oxygen bonding, increased entropy from carbonate decomposition, and careful compositional control to stabilize the perovskite phase and phase boundaries. The kinetics of KNNBCT formation describes how fast and by what mechanisms the desired phases form during calcination and sintering, while thermodynamics tells whether potassium, sodium, niobate, barium, zirconate, titanate can form. Kinetics determines how efficiently and completely it forms. Kinetics I have explained earlier. Now, shortly, solid state diffusion, carbonate decomposition rate, nucleation and growth, grain growth kinetics, and alkali volatility effects explain the kinetics. Basically, KNNBCT kinetics is governed by diffusion controlled solid state reactions, carbonate decomposition rates, nucleation and grain growth behavior, and defect assisted transport, all of which must be carefully controlled to achieve dense phase pure ceramics with optimal piezoelectric performance. If we talk about the different component ratios that are present in material, KNNBCT is typically composed of sodium, potassium, sodium, niobium oxide. Concentrations are written here, modified with 2 to 10 mole percentage barium, zirconate, titanate oxide component, and their typical ratios are sodium and potassium and sodium a 1:1 ratio, um, potassium sodium niobate and barium zirconate titanate 95 to 5 percentage, zirconium and titanium having equal to molar concentration 0.2 to 0.8 and 0.5 to 0.5, barium content 2 to 6 mole percentage, and niobium content 90 to 97 mole percentage. The properties of this material, such as its piezoelectricity, transparency, and energy storage capacity, change significantly depending on the component ratio, typically represented as 1 minus x KNN x BZT. Phase evolution and with ratios. As the BCT content X increases, the crystal structure undergoes a series of transitions. These transitions are crucial because the highest performance often occurs at the phase boundary where multiple structures coexist. Like if x is equal to 0, there is no BCT component, then a crystal structure orthodrombic and its characteristic pure KNN. If X having if the material having X constant mole composition 0.01 to 0.03, then its crystal structure is orthodrombic and rhombohedral, and its characteristic is that its optimal piezoelectricity shown by the material. If X is equal to 0.05 to 0.10, then its crystal structure is rhombohedral and tetragonal, and increased transparency is shown by the material. And if X greater than 0.15, then its crystal structure is cubic and it behave a ferroelectric material. Key properties changes by changing the composition ratios By changing the ratios, a property of material changes like piezoelectric coefficient values measure coefficient also changes like values measure how efficiently the material converts mechanical stress into electricity. Low PCT like X approximately 0.02 reaches a peak due to easier to manual motion at the phase boundary, and high BCT X greater than zero point 0.1, the value drops significantly as the material transitions towards a cubic crystal structure and non-polar phase, and material behaves ferroelectric. Energy storage and transparency. High BCT like X is equal to 0 0.1. This specific ratio is often cited for energy storage capacitors. The addition of BCT reduces the grain size to which 0 0.9 micrometer, which increases the breakdown strength. Optical clarity. If concentration of X is 0 0.1, the material can achieve transparency up to 69% in the near infrared region, making it useful for electro-optic windows. And temperature stability. Adding BCT generally lowers the Curie temperature, while pure KNN has a Curie temperature around 420. Adding BCT moves this temperature downward. Engineers must balance the high performance of the phase boundary with the need for a stable operating temperature range. Here is a table shown comparing comparative material properties of lead zirconate titanate and the material KNNBCT, potassium sodium niobate, barium zirconate titanate. Piezoelectric constant, Curie temperature, density, transparency, lead content, and energy storage density. These properties are comparatively shown here. Like piezoelectric constant in case of PCT 400 to 650 picocoulombs picocoulombs per Newton, and in case of KN and BCT optimized 300 to 700 picocoulombs per Newton. And efficiency of electromechanical conversion also increases in case of KN and BCT. Other properties like Curie temperature, density, transparency, lead content in case of lead zirconate titanate is 60% by weightage, and in case of KNN BCT material it's 0% by weightage. So environmental and human health safety linked through KNN BCT. Energy storage density a variable in case of BCT and in case of K, and then in case of PCT and in case of K and then BCT 2.16, and it involves in the capacitor applications like pulse power and use of this material in capacitor. If we talk about the AI and machine learning in the processing of in the synthesis of material KNNBCT, are we the complexity of the KNNBCT system, characterized by multiple dopant interactions and highly sensitive processing windows, makes traditional experimental discovery exceptionally slow and resource intensive. Machine learning has emerged as a transformative methodology for navigating this high dimensional material space. AI and intelligent manufacturing play an important role in the development of KNNBCT lead free piezoceramics due to the complexity of their composition and processing. Machine learning algorithms are used to optimize compositional ratios, sintering temperature, and atmosphere to achieve high piezoelectric coefficients and phase purity with minimal experimental trials. AI guided process control control helps mitigate alkali volatilization during calcination and sintering, which is a major challenge in KNN based ceramics. Intelligent manufacturing techniques such as additive manufacturing and spark plasma sintering enable precise shape control, high densification, and reduced processing time. Digital twins and data driven models further improve reproducibility, scalability, and quality control, accelerating the industrial adoption of KNNBCT materials. Data driven compositional design researchers have developed machine learning models based on large datasets extracted from decades of literature. One such study utilized triple three data points selected from over 2000 peer reviewed publications to build a model that guides the design of new perovskite materials. These models can predict the piezoelectric coefficient and distinguish between different phase structures such as PPB with high accuracy. Feature engineering and predictive analysis. Effective machine learning in piezoceramic relies on feature engineering, where physical properties of the constituent ions, such as atomic radii, electronegativity, are used as descriptors. Regression learning, classification learning, and optimization are used in feature engineering and predictive analysis. If we talk about the results of AI integration, then the synergy of machine learning and experimental validation has led to breakthroughs such as the discovery of BNT based ceramics with a giant strain of 1.12% and the development of structural gradient KNN ceramics with superior temperature reliability. By using a data driven approach, researchers can achieve in months what previously took years of trial and error experimentation. If we talk about the technical challenges and future recommendations, while KNNBCT ceramics have demonstrated performance comparable to PCT in laboratory settings, several hurdles remain for large-scale industrial adoption. Critical challenges like stoichiometry control, thermal stability trade-off, mechanical quality factor, and reproducibility and scalability are the critical challenges. Stoichiometric control, the preservation of the sodium and potassium ratio is extremely difficult at high temperatures. Alkali loss not only creates secondary phases but also leads to increased conduction, leakage current, and dielectric loss. Thermal stability, like strategies used to maximize piezoelectric coefficients such as constructing an rhombohedral and tetragonal phase boundary near room temperature, often lead to significant reduction in the Curie temperature. This limits the device's ability to operate in high temperature environments without depolarizing. Mechanical quality factor, while soft KNN material are advanced, the development of hard KNN based ceramic uh, with high mechanical quality factor greater than 500 remains a challenge. Current hardening strategies involving acceptor doping like manganese or iron ions often cause a striking and deterioration of D33 piezoelectric coefficient. Reproducibility and scalability. The narrow sintering temperature range, often only a few 10 degrees Celsius wide, makes it difficult to produce uniform large scale components in conventional industrial kilns. Strategic recommendations: advanced sintering adoption, multifunctional development, texture engineering expansion, and defect chemistry engineering are strategic future recommendations to deal the challenges. Advanced sintering adoption: industries should transition toward two-step sintering and microwave sintering to achieve high density and uniform microstructures while minimizing alkali evaporation. Multifunctional development: research should focus on transparent energy storage ceramics. The synergy of high breakdown fields and optical transparency opens new markets in optoelectronic pulse capacitors and transparent actuators. Texture engineering expansion: the use of reactive templated grain growth should be scaled. Textured ceramics consistently show superior properties compared to isotropic versions. Defect chemistry engineering: future work must explore defect dipole engineering to simultaneously improve piezoelectricity and temperature stability, potentially narrowing the gap between lead free and lead based materials. If we talk about the applications of this piezoceramic material, lead-free KNPCT materials are not merely laboratory curiosities, they are foundational to a new generation of smart devices. Healthcare and biomedical imaging, they use a high frequency ultrasonic imaging transducers for medical diagnostics. Why they are used? Because they exhibit high electromechanical coupling and high center frequencies, allowing for improved spatial resolution in imaging. And other than biocompatibility of KNN ensures that even if used in implanted devices like neural stimulators or pacemakers, there is no risk of toxic lead leaching into the bloodstream. Now, industrial and automotive systems, KNNBCT material knock sensors for engines and acceleration sensors for machinery and health monitoring. Canon based materials are used because they have high sound speed and favorable dielectric constants, excellent for high frequency vibration sensing. That's the reason they are used in automotive systems. They are ideal for weight sensitive aerospace components. Energy harvesting and smart infrastructure. They are used as vibration power generator placed under dance floors, corridors, and aircraft panels. The lightweight nature and fatigue resistance of modified KNN allowed these harvesters to be integrated into environments where heavy lead based materials were previously impractical. If we talk about high performance capacitors, then pulsed power systems, KNN BCT material use high breakdown strength. The addition of BCT act as a grain growth inhibitor, reducing grain size to the submicron level. Smaller grains creates more grain boundaries, which act as a barrier to electrical breakdown, allowing the capacitor to withstand high voltages. Lead-free ceramic capacitors. KNNBCT is lead-free perovskite ceramic combining high dielectric permittivity, strong piezoelectric response, and good energy storage density, making it suitable for capacitor and actuator technologies. If we talk about the structure property strategies, then nanodomain, polymorphic nanodomain engineering, grain size, grain orientation engineering, dielectric regulation, band gap tuning, and core shell structures. These structure property strategies are used in lead free ceramic capacitors. As shown in the figure, different structure property strategies like grain orientation engineering, nanodomain, nanodomain engineering, band gap regulation, core shell structure, and other strategies are used in lead free capacitors. That lead free capacitors are used in aerospace, high temperature stability and vibration sensing using KN and BCT piezoelectric actuators and sensors. Power grid lead free dielectric capacitors for pulse power systems and smart grid monitoring. Consumer electronics, and also in electric vehicles, energy storage capacitors, vibration sensors, and ultrasonic actuators with high reliability. If we talk about in medical and industrial transducers, then its ratio of KNN-BCT approximately 0.02% X when BCT component use. In medical and industrial transducers, KNN-BCT used high frequency ultrasounds, vital heart monitors, and non destructive testings. Due to optimal piezoelectric coefficient and high Curie temperature, KNN-BCT material is used in medical and industrial transducers. In microactuators and inkjets, a smartphone camera, autofocus, inkjet printer heads, and micropumps, Canon BCT material use large field induced strain and lead free compliance are the reasoning for application of Canon BCT material in microactuators and inkjets. If we talk about the link of KNN BCT material with SDGs, United Nations Sustainable Development Goals, the development and deployment of KNN BCT materials represent a critical technological shift that aligns with the global agenda for sustainable development. Goal 3, good health and well being. The most direct impact of KNN-BCT is the elimination of lead from the production cycle and the environment. Lead exposure is linked to cognitive dysfunction and neurological disorders even at low concentrations. Transforming to lead-free ceramics prevents toxic heavy metals from entering global soil and water systems through e-waste. Furthermore, the advancement of biocompatible KNN-based medical transducers directly improves diagnostic capabilities for early disease detection. Goal 9, Industry Innovation and Infrastructure. Lead free piezo ceramics represent a cornerstone of sustainable industrialization. The research into these materials has driven innovations in nanotechnology, advanced sintering, and AI driven materials discovery. By providing high performance alternatives that meet environmental regulations, KNNBCT enables the electronics industry to build resilient infrastructure that is both technologically advanced and ecologically responsible. Goal 12, Responsible Consumption and Production. Target 12 of the SDGs focuses on the sound management of chemicals and waste. Traditional PCT manufacturing is energy intensive and produces hazardous waste. Life cycle assessments show that KNN based ceramics impose significantly fewer risks on human health and the environment, with an overall impact only 28% of that PCT ceramics. Furthermore, the energy harvesting capabilities of KNN material contribute to resource saving by reducing the dependence on primary batteries for sensors and IoT devices. Climate action and life on land, goal 13 and 15. How can and PCT material relate to this goal? Piezoelectric energy harvesting from ambient vibrations offers a localized carbon-free energy source for low-power devices, contributing to climate mitigation efforts. Additionally, the non-toxic nature of KNNBCT protects terrestrial ecosystems from the degradation associated with the disposal of lead-containing electronics, thereby preserving biodiversity and soil quality. The transition from, if we talk about the conclusion, the transition from lead, zirconate, titanate, lead-free potassium, sodium niobate systems, particularly those modified with barium, zirconate, titanate, is an environmental necessity and a technological opportunity. Through a combination of advanced phase boundary engineering, meticulous solid state synthesis, and the application of cutting edge AI models, the performance gap that once favored lead based materials is rapidly closing. The chemical evolution of these materials, from the careful decomposition of carbonates to the high temperature formation of complex perovskite structures, requires a high degree of precision to maintain stoichiometry and density. The implementation of modern sintering techniques like two-step sintering and spark plasma sintering has already demonstrated that high piezoelectric coefficients can be paired with industrial stability. Looking ahead, the integration of KNNBCT into biomedical, industrial, and consumer applications will be the primary driver of market growth, with the global lead free market expected to reach nearly $550 million by 2030. While technical challenges such as alkali volatility and temperature dependent stability remain, they are not insurmountable. The continued use of data-driven material discovery and industry's alignment with the United Nations Sustainable Development Goals with, will ensure that the future of piezoelectric technology is not only efficient and precise but also profoundly sustainable for the planet and human health. The roadmap for future research must prioritize the development of multifunctional materials that offer a balance of high D33, uh, high piezoelectric coefficient, Curie temperature, and energy storage efficiency, ultimately providing a comprehensive and permanent alternative to lead based electronics. Thank you. It's all about my topic.